first trial, make sure to do it on your own, and it's good for plasticity, right? Brain plasticity. AI is not good to train the plasticity of the brain. So make sure at least for the first trial that you do that on your own. And what else? Okay, someone asked me an interesting question. Let's say you go from rest, so initial velocity is 0, and you know the final velocity. So final velocity, let's say 56 miles per hour versus 28 miles per hour. By how much by which factor the displacement or the range will increase? How farther you will get? Okay, it's one question in the homework. So in that case, you see that the velocity here is multiplied by 2. So you can use that equation here. The final velocity equals initial square, because there is no time, okay, times 2 times delta x. So for the same acceleration, you see that if you multiply if the final velocity happens to be multiplied by 2, that means that delta x is multiplied by 4, because there is a square here. I'm just showing you how you can reason, think, instead of doing all. Just about vector, someone asked me also a question. Bless you. So if you have a vector A, okay, so you have a tail and a head, the magnitude and the direction. So that will be the direction. I can cut and paste that vector anywhere I want, as long as they are parallel to each other. So same direction, same magnitude. Okay, it will be the same vector. They're all identical. It's the same vector, right? So I can cut and paste. So usually when you have a vector, you will cut and paste your vector, okay, to have it in a x, y coordinate system, and to make sure that the tail is attached to the origin. That point here will have 2 coordinates. That will be the x component of the vector. That will be the y component of the vector. So my point is you can cut and paste. And then the components, you go from the tail to the head. So for conceptual questions, sometimes it's useful to remember that you go from the tail to the head. So then first you run. So that will be your x component, and then you rise. Or you can rise and then you run. So it makes a parallelogram, and that will be your angle theta. Okay, so if the angle, if you have a vector like this, b, okay, so same thing, you run because you want to go from the tail to the head. So in that case, you run this way, and instead of rising, obviously you're gonna fall. But it's the same idea, right? So that will be your y component, that will be your x component, and you have a parallelogram. Again, that point here, that will be your x component and your y component. Okay? The other thing I want to bring your attention to is that if I make a vector exactly parallel to this one, but in the opposite direction, that will be minus a. I cannot say minus, like if it's 600 miles, that's not minus 600 miles, it's just minus a. Okay, you multiply by a minus 1, you flip it. Just flip it. Agree? So that will be minus 1. So that's how we can subtract vector, right? So if you have, for example, if you have b minus a, you can turn that in a sum. So that will be b plus minus a. So you are adding b and a that has been flipped. So you can turn subtraction into addition. I told you to go over the first unit of your textbook, or any textbook will have a first unit and they talk about vectors. It's very important, especially if you go, you will have to take Calc 3 or Calc 4, I forgot the name. Well, you're going to do vector analysis. So, and I have also 2 YouTube videos, very nice, in a Dropbox. You need to know how to add vectors, subtract vectors, find the components. Another thing about vectors, if you have a vector A, and you're going to say, what is 3A? So now you multiply by a scalar. What does that mean? You take the same A, this is A, and you're multiplying by 3, that's going to be 3A. Okay, so that's called multiplying by a scalar. You don't change the direction, you just make it 3 times larger. Is that clear? So, for example, Newton's second law says F equals ma. So a force and an acceleration have the same direction, except that here you multiply by a scalar. Okay, so for example, if you have a mass of, I don't know, 3 kilograms, and this is your acceleration, the force will be 1, 2, 3. Okay, so that will be your force. So that's why I told you before that the force is an acceleration per unit mass. It's like a unit vector here, right? So acceleration is a force per unit force. So if there is a car and the car is braking, so there is a force in this direction because of the brake, that means the acceleration is in this direction. They have the same direction. Is that clear? And then we're going to learn that that's one way to multiply vectors. See, just multiply by the scalar. And then we learn that you have 2 other ways. One way will be called the dot product, and the other way will be called the cross product. So anyway, that was a parenthesis. So let's go back to vector component. So again, any vector, you need to attach it to the origin, the tail. That will be the x component, that will be the y component. Now, if you are not, and by the way, first quadrant, if it's pointing this way, second, third, fourth quadrant. Sometimes it's useful to remember that, okay? So if it's pointing in this direction, it's in the fourth quadrant. Now, if you are uncertain about your trick, remember that if you use the standard notation, so if you go from the positive x-axis and you go counterclockwise, that will be your angle here, 346. The x component is always a cosine, and the y component is always a sine. You have to have in your head the polar graph. So that's why you can go from the standard notation in x, y coordinate system to a polar notation. Agree? So I'm just reviewing. And then someone else asked me a question. So projectile motion sometimes is not no, that's the advanced one. I like the noise it makes. This is the baby one. So let's look at the baby one. So the banana, we did that. We did the banana red. So something which is not that intuitive, if the launch velocity is horizontal, okay, so the launch angle is horizontal. It doesn't matter how hard it's being pushed forward, they both reach the ground at the same time. So it's not that obvious. Someone could not understand that, but the vertical motion, if you look at the vertical motion, you see they are both falling by the same amount. So t equals 0, t equals 0. After 1 second, it's falling 1. This one is falling 1. After another second, this one is falling 3. This one is falling 3. Another second, this one is falling 5. And this one is falling 5. So they will be always at the same height above the ground. Okay, that was Galileo who discovered the odd numbers rule. Okay, so 1, you fall 1, and then you fall 3, and then you fall 5. So you can see that here. The range won't be the same, obviously. If the velocity here is multiplied by 3, okay, that velocity is 3 times larger than that velocity. So the range will be, you can see that this is 1, and that will be 1, 2, 3. So along the horizontal, it will go 3 times farther. Are we good? Okay, I don't know where I stopped. There. Okay, so now we did that last time. So far, projectile motion, we just focused on horizontal initial velocity, but now we're gonna see that here you can have an angle here, right? So the velocity can be, the projectile can be launched at an angle. In real life, you see it's beautiful projectile motion here. So in that case, along the vertical, we will be in a situation of up and down, tossing. So before, along the vertical, it was just drop. Or, no, you could be also mad if you toss. You can do it this way, but just down, right? But in that case, yes, I guess you are also mad, but you are mad at an angle, right? So it's going to go up and down. Or you are mad with a upward velocity, right? So you go up and down. So in this case, you see what it's doing along the vertical is going to go up and down, not just down. So along the horizontal, the velocity does not change, which is now you know it's the x component of the velocity. Along the vertical, the y component of velocity is going to decrease by 10 every second, get to 0, and then increase by 10 every second. So if I try to trick you and I say at the top of the trajectory, can I say the velocity is 0 here? Very good. Okay. The velocity is not 0, only the y component of velocity. So if you need to find the height, you're going to use the vertical equations, and you're going to say the y component is 0 at the top, but not the x component. Okay? And you see, this is just a mathematical trick, because in the real life, when you hit a football, you know, you're not going to decompose in your head, you know, x component, y component. It's a mathematical trick to make it easier to solve, to predict where the football is going to land, how high it's going to go, and then they do software to help the athletes, you know, uh, performing better. But it's in reality, you're not decomposing your vector into components, right? You do it just to solve the problem. Okay, so if I have I think I have an app. Gosh. Projectile. I don't know where is my app, but It's okay, I have it here. Okay, so this is, you have a launch velocity. So it has, you can attach a x, y coordinate system here at the tail. It has a x component. So that will stay the same for the whole time. And it has a y component that will be the initial velocity along the vertical. So toss, okay, the tossing velocities go up and then it goes down. And if you do fire, look at the y component, 0, and then it's going to increase, 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 increase again. Okay? Yes. And
X has no acceleration, but obviously the Y does because of gravity.
exactly. Because the two motions happen at the same time, but along the x-axis there is no acceleration, so the component of the velocity will stay the same. It's not that obvious. You need a special physics glasses to see that. So I hope you are seeing it. See, along the x, it's moving it's cruising along the x, but along the y, it's going up and down. I can increase the angle, so it's going to go higher, 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 slow down, and then the component will increase again. Do you see that? So we're going to have two sets of equations. Okay, you can see that this here will be the initial velocity, but you're going to break it into its components. How fast is going forward? So how much of that velocity is along the x-axis? How much of that velocity is along the y-axis? Along the y is decreasing, get to 0 is going to increase. Along the x, it stays the same. Agree? So if you have a velocity of 50, you need to find the x component. So again, you go from the tail to the head. So that will be 50 cosine 60 is 25. 50 sine 60 is 43. So you're going to take those two numbers and place that in your table. X-axis, y-axis. I thought I changed that. Okay, let's not worry about that. So again, you're going to have two sets of equations, one for the x and one for the y. Agree? It's very easy. So if I try to trick you, at point A, where is the acceleration? What is the direction? A, B, C, or D? B, always B. That's going to be B, and that's going to be B. Acceleration is always pointing down because acceleration is a force due to gravity per unit mass. So gravity never, never, ever gives up on you. So always, Earth is always calling you back. Go. Mostly you're going to do the problems, right, on your own for the assignment. But I just want to show you the methodology. So let's do this one. That comes from an algebra-based book. But I think it's good to have first the fundamentals and then you can make it harder. Okay, why don't you try to do it? So what do we know? We know that the velocity here is 22. So that's 22 meters per second. That angle here is 40 degrees. So initial condition, velocity initial is 22. How much of what? Which way? Standard notation, I know it's counterclockwise. And the first thing they want is to find For example, how high, maximum height. So along the y-axis is going up and down. So here, the initial velocity, no, the x component stays the same, but I see that the y component here equals 0. And the x component is always the same, right? 22 cosine 40. So how are you going to do that? You're going to divide in two components. You're going to say x-axis, y-axis. And now, along the y-axis, we are in a tossing situation. So you have an initial velocity, it goes up, stop, and come back. X-axis, it's always the same thing. You always have the same equation because it's cruising. Projectile motion x-axis is cruising. So the initial velocity along the x-axis, you can put a x, but you don't have to because you remember it's here. So it's going to be 22 cosine 40. Agree? That will be always the first step. Cosine for the x component, sine for the y component, as long as you use the standard notation, and you do it as I'm doing it. So it will be easier. You don't have to worry about chemistry and this and that. Do it, everyone. Get a calculator. Yeah, good. So it's 17. This one, initial condition, it's going to be a sine because I am in standard notation, so I don't have to worry. Always you do that. The first step you do is to do that. That's going to be 14. Always, that will be your first step. Until now, the initial velocity here was 0 because the velocity was along the horizontal. Next step, always, negative 10. Always. And you decide that up is plus, down is minus, left is minus. Always. And you always have delta x equals v0x, right, times t. Always, projectile motion, always. Okay? So 1, 2. So now we can get t, or the issue with t is that we have an annoying quadratic equation. So let's first find the maximum height, meaning find, very good, delta y. And what's happening at the top? Equals to 0, right? So the y component here equals to 0 at the top. That will be the top of the trajectory. I know that the height at that point, there is no y component. You can see that here because it's going up and down, right? So at the top here, there is no y component. It's totally independent from each other. Okay, so you can use the equation like we have done before. Final square equals initial square minus 20 delta y. Okay, 2 times a. Do you agree? Right? Don't, yeah, but the acceleration is negative. So 2 times acceleration. Do you agree? So final velocity is 0. So there is nothing new. You have done that over and over again. Don't use AI because otherwise you don't know what I'm talking about. So delta y equals 14 square over 20.
196.
196?
196 is 14 squared, and then when you divide that by 20, it's 9.8.
Okay, and then you take the square root. No,
No.
no, you don't take the square root. So you do 14 squared divided by 20. What do you get?
498.
9.8? So 10 meters. Agree? Just happened. 10 meters here. Okay, so that will be the maximum height. Okay, so that will be 90. Okay, what else can we do? Find the time it takes to go up.
Just accelerate like 1 second to get here, second to come back down.
Oh, yes. One delta y 10 meters. But let's find the time first. 10 meters up. Do you all agree? Okay, so I'm gonna move here. So y axis, x axis, because I don't have enough space. How can you find the time it takes? Forget that we are in x, y. Just focus on y. What is it that we can use to find the time? So it's tossing. Here you are a tossing situation. Forget about the projectile motion. It's just tossing. What's happening at the top? It's at rest, right?
Cinematic equation.
Yes. So the change in velocity, okay? Do you agree? There is nothing new here. You ignore this one. You take a post-it and you hide it. And here you are just in a tossing situation. How long does it take to reach the top? So final is 0, initial is what? 14 minus 10t. So t up equals, okay, which is 1.4 seconds. Do you agree? So the time to go down is also the same, very good. So the time for flight will be 2.8 seconds. Do you agree? What else can we find? We can find the range, right? So you know it makes like a little break, little tunnel. Boom, 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 boom. Yay! So the time of flight, 2.8 seconds. So the time it takes to go back and hit the ground is 2.8. What's going to be the delta x? So you go back here. Now we are along the x-axis. You shift the post-it, so you don't care about that. Forget about that. You are just cruising along the x-axis. Huh? So it's going to be delta x equals 17 times 2.8. Always, always, always projectile motion. You have that equation here. Always, always, always projectile motion. Here you are either going up and down or you're just going down. Is that 48? Are you with me? So if you follow that formalism, it's not that hard, right? Once you have laid down your initial conditions. So if you take a DFAQ class, this is called the initial condition. And then you see it's not that hard. Okay, so you have to understand it takes the same time. If it's a symmetry, if you have a symmetry, it takes as much time to go up that it takes to go down. Yes? Okay, let's see. I want to find the y. By the way, ca can you tell me what's going to be the displacement between here and there? The y displacement. 0. Very good. Excellent. You go back to the same level, right? They ignore each other up and down. And delta x here, the range is not 0, obviously. But along the y, you just go up and down. This is tossing, and this is just cruising. So the y, the final velocity along the y is going to be what? Initial minus 10t. So initial is 14 minus, so V final is negative. Are you sure? 28 minus 14. Negative 14, right? It makes sense because everything is symmetric and there is no resistance. So here you start with 14 and here you have 14. What's going to be the y component? So before it hits the ground. So the x component will be, does it change? Is the velocity along the x changing? So it's going to be 17. So here we have 17. So obviously, without doing the computation, but you can do the computation, what do you think it's going to be the final velocity here? Exactly, 22, not negative, 22. If it was negative, it will be the opposite direction. But very good, it's going to be, so this is 14 here. That's going to be your 22. If you don't believe me, you do Pythagorean theorem. You're going to do square root of 17 square plus 14 square. And obviously, you can find that angle here, which will be also 40 degrees. Okay? Yes.
In this case, is it usually just safe to assume that the final velocities are equal to the initial velocity?
Yes. It only if it hits the ground. So if it go back to the same place. Which won't be the case, for example, if you just like you throw something here that end up on maybe somewhere there. I don't know what it is. It's a hill. So in that case, it won't be the case, right? Because in that case, you're gonna have your what is it for 17, but the y component will be smaller than 14. So in that case, to find the velocity, you will have to find that vector here, which is tangent to the trajectory. So that will be the instantaneous velocity, tangent, right? So maybe that's going to be, I don't know, 10, for example. So you will have to use Pythagorean theorem, and you can find that angle there. Okay, so it's a good question. Everyone is good? So again, if I like this picture, because you see, at a given time, you can find the x component, which stays the same because it's cruising. And you can find the y component. And the y component is changing at a rate of negative 10 every second. So the y component decrease, get to 0, increase, increase, increase. Okay, so along the y is going to go up and down. And in that case, you see, actually it's a good question, because in that case, is the final velocity the same as the initial? No, because you start from higher, right? So here it's going to be the same, but there you see the final velocity along the y is going to be larger. And because that, the velocity will be larger. So you see, I hope you appreciate the deterministic approach, right? That's classical physics. We were able to predict everything here. Even if it gets more complicated with air resistance, you can still predict where it's going to land. Thanks to Newton. That's enough to go to the moon. Okay. Oh, yeah, you see, we were right. So here I have everything details. Delta y equals 10 meters. That I found very funny, but that's my humor. It's a weird humor. So I keep that for, I won't be here October 2nd. So that, yeah, no, you say, oh no. Did you say, oh no? Or did you say, yeah? Oh no, right? Okay, so it will be just after the test, but don't worry, I will post something to do so you don't get bored. So that will be the range. Again, that will be the height. Uh, so there was a video. That's a very old video. And you can appreciate how the projectile motion is everywhere in the real life. Ubiquitous is the word. So I don't know if you know, this is a church on top of a hill, and it's called Sacré-Cœur. So it's a very famous place in Paris. And to get there, you have to go upstairs, stairs. You know, it's very high. Or you can cheat and take. I think there was a telepheric or something, but it's a beautiful projectile motion. It's his mom. Look, the launch velocity. Did you see? It goes up and down. So it's not horizontal, right? There was a launch velocity, so it goes to a maximum height and goes down. So 2011, that's a long time ago. But he did exactly this. Here, he did this. Little angle here, up and then down. You need to have a strong stomach. Okay, so if you do the math, if you like math, I invite you. We do it with numbers, but you can do it algebraically, doing the same thing that we did, but you do it algebraically without plugging numbers. And if you do that, you will get that range here will be the initial velocity square. So it's proportional to the square of the initial uh, velocity, so v sub 0. Okay, so the launch velocity. We are talking about the launch velocity, not the x or the y component. Sine 2 theta. So sine is always smaller than 1 or equals to 1. So if you want to make the range maximum, you want to have the sine equals to what? Huh? So, yeah, so in degrees. 90 degrees. Okay, so you want sine 90 will be 1. So that will be the maximum range. So if twice the launch velocity equals 90, the launch angle will be equals to 45. Very good. So when the angle is 45 degrees, it's going to reach the maximum range. If you are not convinced, you can play with a hose. I don't know if I have. Uh, see, if it's exactly 45 degrees, that's the farthest you will reach. It's a beautiful projectile motion. It's a beautiful parabola. You see, that will be smaller, obviously. And if you increase the launch velocity, it's going to go higher, obviously, but not as far. So really, physics should be hands-on. You should do it hands-on and then do the math. So anyway, 45 degrees largest range. Now you can check that on your own. If you do 20 and 70, the range will be the same. Because sine of 40 will be the same as the sine of so the sine of 2 times 20 will be the same as the sine at 2 times 70. So the range will be the same. So that number here will be the same if the angle add up to 90 degrees. 20 plus 70 is 90, 60 plus 30 is 90. You can check that on your own for the same initial velocity v sub 0. So it's just math. So we need math. There is no way around. You see, mathematics here, equations tell you stories. Tells the story here that 45 degrees will get you to the larger range. And if you do the math and you malax and you massage, that will be the maximum height. There is also an equation for that. Okay, you just have to do it algebraically. Since you are engineers, you should try to do it and you get to that. To get to here, you have to remember in math that 2 sine times 2 cosine, 2 times sine and times cosine is the same thing as sine 2 theta from your geometry class. So anyway, so here I do the math. I didn't do it, I found it. So I don't have to do it. That will be the range and that will be the height. Agree? Now this in math, if you take a class in algebra, along the y, along the x, you have two equations as a function of time. So in math, they call that parametric equation. X depends on the time, y depends on the time. Now what you can do, isolate t, you isolate t, plugging it in here, and you have the equation of the parabola. Isn't that beautiful? Okay, it's very elegant, it's very nice, right? So again, parametric equation. This is for the x motion, forward, constant velocity. This is for the y motion. You plug the time into here and you get your equation, the equation of a parabola, which is everywhere. Okay, so I invite you, open your textbook, look how to do the math algebraically, but it's just math. And then we go back to Usain Bolt, but I'm not going to go into details. So they did a study on him because he was into what is called track. Isn't that right? He break world records because he was able to run really fast, but he was able to deliver a huge amount of energy in a very small amount of time. So his muscles were very, very special. They call that fast twitching muscles. So anyway, so they wanted to know if he had decided to change discipline. So instead of running, now he wants to go into the long jump physics, long jump discipline for the Olympics, right? Will he be able to break the record as well? And I'm not going to go into details, but the thing that you have to understand, and I just talked about it before, is that the range, so How far you can go by jumping depends on the speed square. That square make a huge of difference, which means if you multiply the speed by 2, the range will be multiplied by 4. If you multiply the speed by 3, the range will be multiplied by not 6, don't tell me 6, 9. Multiplied by 5, the range will be multiplied by 25. The square is very important. Each time you see a square, that means something. Okay, so then it depends on the angle, right? So you want to have 45 degrees, but that's not human. You cannot get to 45 degrees. So usually you stay at 33 degrees. Everyone will have a 33 degrees. So it really depends on the initial velocity, that velocity, okay? The velocity, the acceleration. How big is the acceleration? So from rest to that velocity, okay? So it means it depends on the muscle, right? Acceleration means force means muscles. If you have enough muscles, then you can reach that velocity when you start your jump, and then you jump. So the velocity of Usain Bolt, they did that distance time. You take the slope, it's about 10 meter per second, which is 25 miles per hour. So he was pretty fast. And if you do the math and you find its range, if he did change to long jump, he will be here and everyone else was there. Okay, so that will be the range, and that will be the initial velocity. So he will be all the way there. But he didn't change, he stayed to his discipline. So my point is that physics, it's everywhere. Uh, there is a homework, not homework, there is a problem in your textbook. It's called 3.6. I don't want to do it. I just want to just lay out how would you do it. So it's a bike. So the velocity is horizontal, and they give you the initial velocity, which is horizontal, which is 9 meters per second, and they want to know that point here. They want to know that point here to be able to find the distance. So can you just lay out the equation? Okay, so let me state that again. Initial velocity here is 9 meters per second. And they want to know at t equals 0.5 second, what's happening. So they want to know that point here. They want to know that point. So what they want is to find that distance here. That's the question. They want to find that distance here. To find that distance here, you need to find the delta x, and you want to find the delta y. And t equals 0.5. So that you have to figure it out yourself, right? When they say find the distance, then you understand that you have to find delta x and delta y. So your textbook have very nice solve problem that you want to do for neuron plasticity. Okay, so let's lay out axis. Okay, so not neuron, I'm spacing out. Along the y, do we have an initial velocity? Does it get mad and push it's himself? No, right? Just going down. So it's like a drop. Okay, always here a equals -1, and initial condition, the time is 0.5 second. Here, the initial velocity is 9, always cruising, and we know the time, because the time is the same. Oh, I cannot, okay, let's do it this way. So if you want to find a distance, I need to find delta x and delta y. Agree? So delta y, you use your kinematic equation, so that will be minus 5, 0.5 squared. Which is negative. Do it. 1.25. Everyone, did you do it? The more you do it here, less you have. Don't fall asleep, right? Stay awake. Delta x equals cruising 9 times 0.5. So delta x equals 4.5. So that point here, okay, has two components. So 4.5 and so it's going to be 4.5 and minus 1.25. Do you agree? So if I want to find that distance here, you just use Pythagorean theorem, right? So the distance will be the square root of, and here I always have students who put the minus outside. Don't put the minus outside. When you have a minus and you square it, you can just forget about the minus because it's being squared. Plus 4.5 squared. So that will be the distance, right? So it's like you have the origin here, you have your point. That's the point P. 4.5 minus 1.2. And you want to find that distance here. So you use Pythagorean theorem. Agree? So D equals 4.7 meters. Okay? And then they want you to find the velocity at that point here. So the velocity is the instantaneous velocity. So that will be the velocity here. But it has two components, right? So it has a x component and a y component. And this is the angle there, alpha. Okay? And you see it's in the fourth quadrant. So I'm going to find the y component. What's the y component? You have the time. V equals initial minus AT. So the y component will be the y component here. After 0.5 seconds, the velocity increases at a rate of minus 10. Negative 5, very good. So negative 5 meter per second, kinematic equation, the y component increases by at a rate of negative 10. The y component increases at a rate of negative 10. The y component increases at a rate of negative 10. And the x component stays the same, which is 9. Agree? So that takes us to the introducing what we're going to do next about adding vectors. So x component 9. So when you have a vector, like we're going to have force is a vector, it's hard to visualize just by giving you the components. because you will need to find a direction. And it's very easy to do a mistake at that point. So the first thing you want to do is a X, Y coordinate system on the side. And you're going to see, okay, this is 9 and this is -5. You attach the tail to the origin here and you're going to make your vector. So that's going to be the velocity here, V. It's the same thing as this one, but it's going to be easier. Because what's going to happen there? Why is it so easy to make it wrong? Because you want to know which angle you want to use. You have two angles here, and they're going to be complementary. So if you use that angle here, which is good for the standard notation, you have to use. How can you find the angle? So you forget about minus or plus, you go back to your trigonometry. So in trigonometry, you have, it's like a right angle here. This is 5, and this is 9, and this is the angle you want. So what is it that you're going to use? SOHCAHTOA. Tangent, right? So you are here. This is you here, right? At the angle. So this here is the opposite. It's opposite across. This here is the adjacent. Opposite relative to you, adjacent relative to you. So we're going to use tau r, right? So alpha equals tan arctangent 5/9. So that's going to be about 29. Okay, so let's say 30 degrees. What's the magnitude of V? So you use Pythagorean theorem. And you forget about the negative, okay, because it's square. Okay, so let's say 10 meters per second. So the final answer, V, has a magnitude of 10 of what? Meter per second. Which way? I cannot put 30 degrees because that will be 30 degrees. What do you think this angle is? Huh? So yes, but we don't want east, west, things like this. So that angle, you have two ways to do it. You can say you go counterclockwise. So that will be what? 3, 3 what? 330, thank you. Okay, that's one way. Or you can say it's negative 30. So you can see that both notation are okay. Or if you have south and east, so that will be south, east. South of east. Yes. Because if you do the negative, it might get you something wrong. So when you find the angle, you forget about the negative. Because that magnitude is 5, this is 9. So you are just back to math. So if when you find an angle with math, there is no minus, right? This is just the opposite and this is just the adjacent. So in trigonometry, if you need to find an angle and it's a right angle triangle, like here, you forget about negative or positive. This is just the opposite and this is just the adjacent. So you have to be careful because that angle here will be 60. So 60 will be if you use the tangent 9/5. So you have to be careful with that. So we are down. So this is negative here. Yes, but it's because at t equals 0 is 0. At t equals 1 is going to be negative 10. At t equals 2 is going to be negative 20. So it's increasing in magnitude, except it's pointing down. This is because we decide that down is negative. So it's always negative 0 minus 10. So because of that, variable velocity equals minus 10t. So v equals minus 10t. So t equals 0 is 0, minus 10, minus 20, minus 30. So magnitude, it increases, but it's down. So in this app, you see that they use a negative number. You can do that as well, right? So I have a vector, you can attach that. It will work also, right? So if you have the origin here, you can do cosine minus 17, and you're going to get the x component. The sine of minus 17, you're going to get the y component. So this notation is kosher. It's fine. Or you can do that notation here with the 346 going counterclockwise. It's good too. This is math. This is not physics. Agree? Okay. I'm glad that you agree. I don't know where we are. Okay, so a little bit of more math. You see that you can divide again your motion into two components. In our case, there is no acceleration along the x, but it doesn't have to be the case. You can have a acceleration along the x. Okay, so in that case, you have three sets of equations for x, three sets of equations for y, and you can pack those two. You see, those two equations you can pack into one. It's a notation that you are packing things together, but you have an x component and then you have a y component. So you pack this into one equation. Likewise, that will be the x displacement, that will be the y displacement, and you pack everything into one equation there. So you're using vector calculus, except here there is a typo. It should be 0. Okay, so we already talked about that. So if you have something going at a constant velocity in that case, you can decompose the motion into two components, and to find the x displacement, which means how far did it go along the horizontal, then you use only the x component of the velocity. How far did the turtle go in this direction, then you can use only the y component of the velocity. Okay. Okay, so it can be useful for people coding, you know, when in sports science, for example, you need to decompose a motion into its components. So, for example, if this guy is running in this direction, so the football that he's holding in his hand will have the same velocity in this direction. Now, if he start to hold the football, that will be the velocity relative to him. So the football is doing two things at the same time. It's moving forward in this direction, but at the same time, it's going perpendicular to the athlete. Okay, so actually it makes sense to you that the football will go along the diagonal. So I don't think the athlete, in their head say, okay, delta x equals vx times t. Oh, but yes, wait, I'm pushing it with an acceleration, so y equals blah blah blah, and I need to compute the distance here to make sure he's gonna be able to catch it. At some point, it's your guts doing the physics, right, and training and practice. But they use software to help training. Okay, so same idea here. We can go back to relative velocity. This airplane is doing two things at the same time. It's moving relative to the wind, relative to the air. Okay, so that will be depending on the engine. So it's the airplane pushing the air push back. At the same time, the wind is pushing, what is it, west? So the airplane will go that way. And then you have a computer that will make sure that you can change the direction and turn in this direction to go straight. Does it make sense? And that's a good introduction to what's coming next. This component here and that component here, what is it doing here? It's called adding vectors. How do you add vectors? You take the first vector, and then you take the second vector on top of the first. This is called tail to head, and that will be the sum of the two vectors. That's why you see that notation. This is called adding vectors. I invite you to look back to the first unit of your textbook or the tutorials that I have. So there is a very cool, this is very cool. Simulation, very nice. Very, 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 very nice here. So what's happening here? The boat, okay, has an engine. So it wants to go, so it's going straight. So in this direction. So the velocity of the boat relative to the river, use a vector velocity. Okay, so it's the velocity of the boat relative to the river. But at the same time, the river is flowing to the right. So what's going to happen to the boat? Does it make sense? Do you see? So it's missing here. The people are waiting for the ferry. And no, I didn't go the right way. So what can I do to fix that? Right? I need to change the angle. I have to go like something this way. Okay. So now this is adding vectors. That will be the velocity of the boat relative to the river, the velocity of the river relative to the ground. And that will be your final velocity. This is called adding vectors, head to tail or tail to head. Okay, let's see. Do you see the direction? Isn't that nice? How lucky you are to have simulation. We didn't have that back then. So again, here it's doing two things at the same time. It's moving relative to the river. The river is moving relative to the ground. That will be the sum of those two vectors. You can think of that as the x component or the y component, x component. Interestingly, if you want to know the time it takes for the boat just to reach the other side here, you just use that velocity. So that velocity will take you, how long does it take to go along the vertical? And if you want to know how far, then you can use that component here. Okay, so this is called adding vectors. So I'm adding this vector to that vector. Okay, same thing here, dung dung. Oh, so if I want to cross the river, that will be the velocity of the boat relative to the river. That will be the river relative to the ground. That will be actually the velocity that it has relative to the ground. So it will go that way. Is that clear? And this is called adding vectors, tail to head. Okay, so again, if you have two vectors, A and B, and you want to add them up, example of the boat or the airplane, you cut one of the vector. It does not matter which one you are cutting, and you're going to paste it on top of the first vector. It's called tail to head. And then you go from the first one, to the first tail to the last head. That will be vector A plus B. Okay, so this is called adding vectors tail to head. Again, the velocity is going this way of the airplane relative to the air. That will be the wind relative to the ground. That will be the velocity of the airplane relative to the ground. So this is called adding vectors. So I take one vector. So let me show you how you do it. You have one vector here. And you have another vector, B. Okay, so let's say you have those two vectors and you want to add them up. So you have two ways to do it. You have the parallelogram way and tail to head. Let's do the tail to head. I'm going to take this vector, I cut, and I place it on top of this vector there. Are you with me? Tail to head. And then I'm connecting this to that, and that will be the sum. That will be called the vector sum. To understand that, you need to have the airplane in your head, right? So the airplane wants to go, it's going this way, and the wind is pushing that way, so the airplane will go that way. Are you with me? So tail to head, the different way to do it, again, you cut and paste here. You attach them by their tail. So that will be called the parallelogram method. And here the diagonal of your parallelogram will be the sum. So that's called the parallelogram method. Yes. That's just the magnitude. Okay, the magnitude. That will be the magnitude. So if I click on it, the magnitude is 10. You have the x component and you have the y component. Any question? Again, you have to look at the tutorial, right? So this is called tail to head. So this is nice. You can do it geometrically with a protractor and a ruler and a pencil, and you can add vectors. But we need a different way to do it. You have to know how to do it algebraically. So look at vector A. See, you have vector A. The magnitude is 12. The direction is 20. How can you find the x component? You do 12 cosine 20. Very good. The y component, you will be 12 sine 20. Okay. I have a vector b. 25 is the magnitude. 60 degrees is the angle. So I'm going to do 25 cosine 60. 25 sine 60. Can you see that you go from the tail to the head, you run and you rise? This is the x component, that will be the y component. From the tail to the head, You run and you rise. This is the x component and the y component. Do you agree? You can always take a y and x coordinate system. So this is the origin, for example. That point here will be 12.5 and 21.7. Agree on that? And then to add them up, you're gonna cut. Doesn't have to be B, you can cut A, but you cut B, for example, here on top of A. Tail to head. Okay? And to find the sum, you go from the tail to the head. So can you tell me, how can I find the component of that sum here? So that component, the component of R. Can you see what the component of R is? Yes, 23 something, right? So to find the x component of R, you just need to add the x component of A plus the x component of B. You see that here, right? The y component of R, you add the components, the y component of A plus the y component of B. Can you see it with your eyes? Okay, you don't need to take an advanced class here. You just see it with your eyes. Okay, make sure you have your glasses on. You see here, this is your y axis. This is your x axis. Okay, so here, that point here will have an x component. You have the x component and the y component. That's the point here. And you see that the x component here, see, all the x-axis here is Rx. And then here you have Ry. And staring at it, you can see that the x component of the sum is the sum of the x component of A plus the x component of B. And the y component of R is the y component of A plus the y component of B. So this is called adding vectors algebraically. You add the individual components. It's easy, right? So if you have a vector, for example, let's take another example, A, 3 minus 2, and B component is 5 and 7, and you want to find the sum, which is also a vector, you just add, that's going to be 8, and that's going to be 5. And the notation will be sum equals A plus B. And you can do it algebraically or you can do it geometrically. B on top of A on top of B, you go from the tail to the head. Agree? So it's not that hard. I should not teach that because this is math. But we need math. Oh, I love the noise. So okay, let's take 2. It's a very satisfying noise. I don't know why. Okay, let's take 2 vector. Okay, put that on. Forget about that. I'm going to take vector A. Okay, do you agree? And each step is 2. So I go from the tail to the head. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. X component is 10. From here, 1, 2, 3, 4. Y component is 4. Do you agree? Yes? And now let's take another component, a vector. Let's take, I don't know, this vector. So first, I'm going to do it geometrically. So I can place my vector here wherever I want. I take vector B. So vector B is going to do this. Vector B is 1, 2, 3, 4, 5, 6, 7, 8. 8 is the x component. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The y component is 10. I'm going to cut B on top of A. Agree? So to do the sum geometrically, I'm going to trace here a line between the tail of the first one to the head of the second one. So you see that the component of the sum is x component of A plus x component of B. See the sum, 10 plus 8 is 18. The y component will be the y component of A plus the y component of B. Okay? And here you don't, that's the dot product. Don't worry, I can go in the polar polar form. And you can also find the magnitude using Pythagorean theorem and the angle relative to the positive x-axis using tangent. At what time the quiz open? Because I forgot. 12:05. Okay, good. So I can do something like this, right? I go from the tail to the head, agree? So x component, y component for A, x component is minus 18 for B, 23 is the y component. So I can find the sum, I just add them up. Okay? No, it's the same. Oh, but a polar graph, if I want to find the polar graph, then I have to take my vector sum that I have found, right? Using the x, y, and then for the polar graph, I have to use, to find the magnitude, I need to use Pythagorean theorem, and to find the angle, I have to use a tangent, like we did with the problem 3.6. So it's a good question. You cannot do, if you want to find the polar graph, the polar form, it doesn't work, right? So you have to go find the x component, find the y component, find the magnitude, and use the tangent. So it doesn't add up here. Only the x component add up. So what it means is that if you have two vectors and you add them up and you have the sum, if you want to find the polar notation, then you have to find the component first, and you need to find the magnitude, which is x squared plus y squared, and you have to find that angle here, which is tan minus 1, in that case, y over x. So you have to find the x and y coordinates, and then you go to the polar form. So we can do that. Can you try to do this one? So need to find the vectors first. So vector A. So you go from the tail to the head. So what's going to be the x component? 3. What about the y component? 4. Very good. What about B? -3. Very good. And the y component? 2. You go from the tail to the head. 2. What about the vector C? 0. And then uh, 1. negative 3. So the sum, which is A plus B plus C, and it's a vector, it's going to be minus 3, 3, 0. So here we have a 0, and here we have 3. So if you can prove that also, adding tail to head. So if I cut this one on top of that one, so that will be vector B, vector A plus C. So then you go tail to head. Here, that will be your sum. So I can do it geometrically, tail to head, but of course, it's easier to do it algebraically. Okay? So this is, it will make your math class easier, right? Because most of you, many of you have to take that calculus class. Now, in your book, they use a different notation. So A is 3, 4. But instead of writing this way, they will write this way. 3i hat plus 4j hat. It means the same thing. But here it's like they are using a sum. Okay, why? Because if you go back to the drawing here, we can define unit vector. So that will be a unit vector I hat. That will be a unit vector j hat. So it's just along the x, and the magnitude is 1. J hat is along the y, and the magnitude is 1. So do you agree that the x component here, so this is the x component, so ax will be 3 times this vector here, right? Convect 4j hat. So it's just another notation. So this is called a unit vector I hat. It's called, this one is j hat, and it just means that the magnitude is 1, and it's showing the direction of the x-axis. This one is showing you the y-axis. So anyway, we'll see that later, but it just means that this is the x component and this is the y component. So you can go from here to there. Okay? So that was math. A lot of math today. I hope I didn't ruin your day or anything. Active.